The rapid evolution of digital technologies has dramatically transformed operational landscapes across industries. Yet, stadium management remains one of the most complex logistical challenges in the modern world, balancing security, accessibility, and fan experience across venues that process tens of thousands of visitors within narrow time windows. Every game day or event presents a multifaceted optimization puzzle. How do you minimize wait times without compromising security? How can you allocate staff efficiently across unpredictable attendance patterns? What's the optimal placement for concessions to maximize both revenue and fan satisfaction? These questions have traditionally been addressed through educated guesswork and incremental adjustments, a process that's not only time-consuming, but inherently limited in its ability to predict outcomes. This is where Simio enters the playing field. Founded by a team of simulation industry pioneers with over 30 years of experience, Simio has established itself as a leader in advanced simulation technology. Our platform builds upon decades of innovation in discrete event simulation methodologies, creating a powerful solution for complex operational challenges. At its core, Simio offers simulation technology designed with both power and simplicity. Our patented object-oriented modeling environment allows users to build sophisticated simulations without extensive programming knowledge. With an intuitive drag-and-drop interface, pre-built object libraries, and intelligent objects, Simio makes advanced simulation accessible to professionals across disciplines, from operations managers to data analysts to facility planners. This user-friendly approach doesn't sacrifice analytical depth. Simio's simulation engine processes complex algorithms and dynamic variables to create accurate, reliable models of real-world systems and their behaviors. A digital twin is far more than just a static model. It is a constantly evolving, active digital counterpart of a physical asset, system, or process. Digital twins process diverse streams of data captured from sensors, IoT devices, and other physical systems, and use this information to replicate current conditions in an intelligent, dynamic digital model. This live feedback loop offers operators immediate visibility into system performance, enabling agile responses to changing conditions. The integration of simulation with operational data creates a powerful predictive tool that transforms how venues plan, manage, and optimize their facilities. For stadium operations, Simio's digital twin technology enables venue managers to test modifications to entry procedures and security configurations without disrupting actual operations, optimize staff deployment based on projected attendance and event-specific variables, identify and eliminate bottlenecks in concourse traffic flow and concession access. Through advanced simulation capabilities, these models perform what-if analyses and conduct stress tests virtually, allowing operators to validate changes before implementation. Venue operators utilizing Simio's simulation technology have achieved remarkable results. Up to 30% reduction in entry wait times, 77% reduction in security screening footprint while maintaining safety standards. These measurable outcomes translate directly to enhanced fan experience and operational cost savings. Simio stands at the forefront of stadium operational excellence, transforming how venues optimize every aspect of the game day experience. Our digital twin platform empowers stadium operators to make data-driven decisions that dramatically enhance fan satisfaction, from the moment they arrive until the final play. For fans, this means less time waiting in lines and more time enjoying the game. For operators, it means maximized revenue, optimized resources, and a competitive edge in an industry where fan experience determines success. In a market projected to reach $38 billion by 2033, Simio's digital twin technology isn't just changing how stadiums operate. It's revolutionizing how millions of fans experience the games they love. Transform your game day operations with digital twins.
And hello, everyone. My name is Drew Rose. I'm a solution engineer here at Simio. So I work with our current and prospective customers on a number of different industries and applications. A little bit about myself. Prior to joining Simio, I graduated from Penn State with a degree in industrial engineering. And that's really where I first found this particular topic to be near and dear to myself. So some undergraduate research was conducted on Beaver Stadium, Penn State's collegiate football venue, And really, I think that's translated now to present state where we get to work on these digital twins and all these different aspects across professional sport and collegiate sport. So today we have a couple different topics that we'll focus on. The first of which is going to be more so focused on the security aspect of how we manage a digital twin. The other is going to be more so focused on internal happenings around the concourse of a particular venue. So with that in mind, we'll touch on some different topics, and we will go and share a good bit of content today. So the first scenario in question today is going to be focused on security operations at a football venue, namely going to be at the Pittsburgh Steelers Acrisure Stadium. Simio being a Pittsburgh-based company, it only makes sense to focus on the local team. A little bit about the system in question and a few of the parameters. So Acrisure Stadium has a capacity of 68,400 individuals. And in this model, we're going to focus on all the different types of ways that fans can get into and at the stadium. So it's a very unique parking situation at the North Shore where the stadium is housed. There are many different small pockets of parking lots, each of which have their own varying size and proximity to the stadium. Additionally, you're not limited to just parking. There's also going to be waterborne and public transit options that are also an option for how fans are getting to the game. And with all those different modes and nuances for how they get to the game, there's 4 different gates of where they can enter. So there's the Gate A East, Gate A West, Gate B, and Gate C. So these are the access points of where fans are going to route towards. And you'll see in the coming moments how they would consider moving to one of the gates relative to where they are arriving from. So the problem statement around that is going to be mainly considering those arrival patterns. So given all the nuance and uniqueness of where fans may come from, what time they may arrive, all the different aspects that would make up a game day, we want to consider how that is going to impact our operation from a security standpoint, getting fans into the game. And this is particularly relevant for this consideration because it is in the best interest of the stadium to get fans in safely and efficiently, because it has been found that if you get fans in prior to a game kicking off and not missing any action, there is increased likelihood of them to go and buy from concessions. Whereas if they were arriving, having a game already kicked off, they're not going to want to further miss more action. So they're going to be more inclined to go to their seats then. So the sooner that fans can get into the stadium, the more revenue that could be generated from the venue. And based on that assumption and based on that goal, what we're going to want to identify is how much security should be allotted to each of those gates, given the variable aspects around them. So while this is focused specifically on security today, this is just going to be a small tip of the iceberg relative to the types of things that could be considered in such a scenario. So we touched on the arrival time distribution, fans arriving, whether that be as the gates arrive or nearing kickoff. There's also going to be a lot of grouping behavior at play. Fans aren't going to travel by themselves. They may arrive with their individuals, friends, family, and there may be grouping behavior. Then as well, you could consider the ticket profile, whether they're going to be lower deck, upper deck, suites. Different types of profiles lend themselves to a different type of consumer. And as well as anyone well knows, going to a sporting event, the queuing behavior may be variable. There may be line hopping, leaving lines, moving lines, a lot of different aspects that can be captured in that regard. And then as well, the screening technology. So what type of metal detector is being used? Is it performing imaging? Is it metal detection? A lot of nuance in that regard. And as well, seeing some of the other aspects, you could talk about false alarms, weather patterns. If it's a cold game, that's more inclined to get fans in quicker. If there's a promotional event, maybe that there's going to be more incentive for fans to get to the game sooner. So we need to ensure that we have the proper staff. So all these could be something that are variable events where it would be difficult to quantify otherwise, not having a simulation tool at the disposal to conduct this analysis. So with all this context, that's where we will now turn towards the model itself and dig into some of the details. So a little bit about the software, and as I get to the main screen here, Simio, as our namesake implies, where it comes from is simulation with intelligent objects, meaning that any system that is being constructed, whether that be in the sports venue or any other industries that require such a tool, we're object-oriented in nature, so that this particular system itself is described of the various objects that you see here on the left. And these are There's various sets of objects that have parameters to them that can be described for an intended purpose. So in this sake, all these different behaviors in the North Shore, we can capture all the different parking lot behaviors with one of these objects. So all of these different colorations that you see here indicate various parking lots that are in this system itself, and they just indicate types of fan profiles. So if there's whether that it is RV lots, purchasing in advance, purchasing day of, season ticket holders, that's just a little bit of context for all those different colors here. And really, when these all get considered against one another, that's going to be how fans are going to route to the game. So you see right of the stadium, there are many more parking lots relative to left. And so when we go into the 3D vision of the system, and Simio is a 2D and 3D object, while we can consider all of Pittsburgh in its entirety, we see the hockey arena here, we see the pristine bridges that you would often travel across as attending a Pittsburgh event, the baseball stadium. We can see that giving all these different parking lots, there's various proximities to the gates of the model itself. So that those 4 gates that we saw on the diagram are played out here. So we see our gate A East, gate A West, and then as well we see our gate C, and then our gate B. So really this allows you to have a strong digital version of a system in reality. And now with this, we can start to set up some of those scenarios that we are questioning and how we would go start to conduct that analysis. This is unique to Pittsburgh, but if you're thinking about your system itself, you would factor in all those different dynamics of how do fans arrive to the game, where can they park, how do you go about parking in that case. That's really a sandbox for you to build out your system at broad scale and capture all those unique behaviors. So when we build out those profiles, the aspect that is also considered is going to be how we introduce data into this model. In that case, that's where we would use this data tab to help define activities that are going to take place. And as I mentioned, we're going to focus on the security in this instance. So really, we want to focus on all the different tasks that need to take place at the security department itself to get fans into the game safely and efficiently. So that's where we would turn to data as an input. And in this case, that's where we can make use of data to capture those variable behaviors. So you would expect that as we go through the security set of tasks, these are the following aspects that can be captured and then incurred throughout the model. So as any fan enters into the system from one of those locations, there's going to be an inspection that's done, detection, and there's also the probabilistic nature of whether or not there's going to be secondary screenings, bag checks, and then ticket scans. So really, if you think about that process as a whole, that's not going to be a statically incurred time for each customer. It's going to be sampled from these distributions so that you get a representative range of what timing may look like in that regard. Then as well, we can also capture from those parking lots, how many fans are we anticipating from each of these lots? So given the proximity, given the size, given the profile of the fans, we can capture all the different nuance that we would expect from each of these parking lot locations. So really, if you filter down to all the different areas, that's going to give you a variable arrival pattern so that across all the different dimensions of the stadium and all the different location and access points, we can anticipate that it's going to be a variable level of demand at each of the gates. They're not going to experience the same level of customer traffic, just given their proximity. We wouldn't expect fans that are parking in the downtown garage to want to go to the far corner to enter. They're likely to enter the one that is closer to them. So those are the types of nuanced behaviors that can also be considered as part of the model. So that's a lot of bit of the setup, and that's really, at least from a broad overview, how we would approach a type of model build, in this case, unique to security. But then when we ultimately want to consider things in full, that's where we would set up our controls. So in this instant, we want to examine how many different security checkpoints do we have at each gate to get customers through the system. So these are the controls that take, with all else being equal, here's how many access points we are allowing at each gate. So at gate A East, there's going to be 15 access points, and as it would imply, we can toggle that amount and see what that impact is for rapid scenario analysis. So when this model initializes, we'll see that as we go in, we're going to see that the game, we're going to assume a 1 o'clock kickoff for a Steeler game. So gates will open at 11 a.m. So as we would imagine that the peak traffic is not going to start right when the gates open. We would imagine as it gets closer and closer to the game, we're going to anticipate more and more customer traffic. So moving around, we see that we have our customers flowing through, and early on in the process, it's going to be very little timing it takes to get through the gate, not a lot of queuing, as would be expected. And moving around, we see all the different activities. See that this gate as well has light traffic. Early on in the operation, pretty smooth way to get in. There's not going to be a lot of wait times that are incurred. As we pan out and move along in the system, we're also going to see, we can get that visual of what is the current wait time at each of the gates. So in this case, early on in the system, we wouldn't expect much of a wait time at each of those gates. But when we move forward into the operation, and we'll fast forward a bit just to get closer to kickoff, I want to fast forward closer to when we have peak arrivals. So given the distribution and the data that we've presented, we're going to imagine that at the 12:45 mark, give or take, that's going to be when we're closer to our peak demand, right? 10 minutes prior to kickoff, we'd imagine that most of the customers are getting into the system around that time. And then when we pause, we can see that given the variables that we've set, what is going to be the current time and system for each of the gates. So zooming in, now we'll go back to our 3D. We can see that relative to all of the locations, Gate A East is experiencing a significant amount of queuing. And then as well, Gate A West, just given the proximity and given the factor that maybe the fans are not incentivized to walk a bit further, we see that there's significant variability as far as wait times are concerned. Then as well, moving to our other areas, we can see that at this gate as well, pretty high demand for entry. And then once more, we'll pivot and look at our Gate B. So as you would imagine, prior to kickoff, once we get closer to the game, we're going to have a bit more traffic to get into the stadium itself. So given this operational challenge, this is being the peak period of when we want to get fans into the game, that's where we would turn to that scenario analysis to start to conduct this work. And before we do so, we want to examine what is going to be the overall metrics of this particular scenario, given the amount of security checkpoints that we've allotted at each of those stations. So when we run this to conclusion here, and we have the run, we're assuming that all of the fans are going to be in at around 2:15. Once we stop, we'll take a look at some of the results that are gathered from the model. So given all that information, this is just going to give us a little bit more of a conclusive data point after the run to identify the different trends that took place in that model. So when we see all the different instances here, we see the time in line per period. So these are 15-minute intervals prior to kickoff. So the period 10 here being the peak period, that being the 12:45 to 1 p.m. period, we can see what those different impacts are. So if I wanted to look, and we see clearly across the board, there's variability from gate to gate as far as how customers are getting into the system. So if I wanted to get a more concentrated view, Gate A East, we see that at its peak, the average wait time was about 6 minutes. Seems relatively healthy. Whereas Gate A West, we never really experienced much of a wait time, which would seem to suggest that we over-allocated the amount of security needed, given the amount of fan traffic that it experiences. But then when we go and look at our Gate B, we see that at its peak, it is nearly 30 minutes worth of wait time. So there's a disproportionate amount of security allocated at each of those different locations. And then also when we get some evidence of the entries per gate, we see that Gate B, relative to where it's located, gets double the fans of Gate A West. So clearly there's some disproportionate amount of allocation that is at present. So that's where we want to turn to see what is the amount of staffing or resources that will be needed to properly satisfy this condition. And that's where we can make use of those controls to really do that analysis in a robust and quick manner, considering all the variability that's in play. And so off of that, that's when we want to turn to scenario analysis. So as I mentioned, we have those various control points of how much allocation we want to devote to each gate. And you can conduct that analysis, and you can set up these scenarios that are going to test side by side, running the same model but with varying amounts of labor. So I could run one scenario testing 15 checkpoints at each gate, or I can test these, or I can test these all manually And you can certainly do so, but especially when we deal with these complex variable dynamic systems, to do so in a manual nature is rather inefficient. And that's where we would turn to optimization to aid in this decision making for us. So to do that, we'll set up our optimization statement and we can set up the parameters of that optimization. So I want to include the following gate allocations to my analysis. And then I want to determine how many checkpoints should I have at each gate with a range of 8 to 22, incrementing by values of 1. So I'm going to set up that parameter for each of my gates. And that's going to generate a set of scenarios for me to run concurrently. And when I do so, it's also going to run those models against a various set of responses. So we're going to be monitoring the wait time at each gate, and that's going to be a value that is output. We're also going to be cognizant of the cost of each scenario because we don't want to have more security than is needed and have redundancy. So we're going to be cognizant of not overspending. But also, given that if we have customers added into the system efficiently, there's going to be additional revenue that we generate from getting customers to go to the concessions prior to going to their seats. So if we see a particular scenario that has fans entered into the system quickly, we're going to experience revenue off of that. So really with that optimization, we have the goals to minimize our various wait times while also maximizing our revenue. So some cost and benefits that are being considered. And with all that set up in mind, that's where we would go and run that analysis, and then it'll be kicked off in that regard. So the optimization is going to automatically generate scenarios for me, and it's going to run through that model, consider all the variability of the parking lots, the arrival times, scanning operations. It's going to run through those scenarios, produce results, and give me a sandbox to give some rapid response analysis. So I won't run this to its completion, just given the sheer volume of scenarios that could be run. But especially if you're an operations manager and you're considering all the different factors that would be a part of your model, really this gives you a lot of opportunity to go and run those scenarios in a rapid manner to try to identify what optimality may look like for your particular system. So I'll let this run for a bit of time, but then I have also, just given being cognizant of time, we can show what a finished result would look like in that regard. So you see that it's running different instances, toggling the amount of security. So we see that if we have 8 checkpoints at Gate A East, we see that the wait time is significantly impacted by that. Whereas if we have 22 checkpoints, we are getting a near zero wait time. So we're going to get that response to those different factors. So we're going to run that, and I will just cancel this. As I mentioned, we can examine the finished scenario. And when we do so, we'll take a look at what those final results look like. So when we run to completion, in this case, we have 300 different scenarios that were generated. It is going to iterate through all the different solution space. And given my different bounds that I've set, any scenario that is out of bounds relative to what my goals are, it's going to be flagged as red. So that's what those red indicators are signifying that scenarios that are infeasible relative to what our goals are. So it's going to iterate through all the different scenarios, consider all the different factors that I've specified, but what it ultimately produces is a single output that is deemed the optimal scenario given the different constraints that I've posed on it. So in scenario 219, you see the checkbox indicates that this, relative to the problem statement, is the optimal scenario given all the different constraints. So when we look at this, we see that each gate with the amount of security that is allocated has wait times underneath 5 minutes for each scenario. And the allocation of each signifies that we have 14 gates, 14 checkpoints at Gate A East, 8 at Gate A West, 22 at Gate B, and 8 at Gate C. So really, we can see that given that amount of demand that was experienced, we're going to allocate differently and according to those different behavioral patterns. And when we see all those different scenarios, that's where we can look at our response results a little bit more detailed to see how did we arrive at this result. So this is showing all the different replications that were run of this model. So given the same variability that was imposed each and every time, this is just going to give us a representative range of what is going to be the different KPIs. So whether that's our concession revenue from scenario to scenario, whether that is our revenue relative to cost, or whether that's the average time in line. This is going to give us a nice representative range with some different statistics that we can determine the confidence interval of, given this scenario's values, what is going to be the mean output of that result. So a lot of different insights that you can gather from this framework, and really a lot of conclusive results that you can get from that. So this is a little bit of how you would consider things in broad terms, especially with these large, complex systems that have a lot of factors at play. Really, this optimization power is really lends itself to understanding these variable environments in great detail. So that's a little bit about this the first scenario, and I'll pause here if there are any questions or anything that's coming to the chat thus far. All right, we'll go ahead. So have another scenario now. So this is more focused on that outside operation, focused on security, but we'll turn now to once we're inside a stadium, how we would consider a particular concourse. And so that's where we'll do a similar type of analysis, but also have some new considerations as part of that. So in this case, we're going to be focused on the concession operations inside a baseball venue. So in this case, the problem statement is focused on the pace of play initiatives that has been imposed by Major League Baseball. So in recent years, there's been an emphasis to shorten the game times and the time that it takes to go through a full 9 innings. And off of that, stadium operators need to be cognizant of, given that we have now a shorter game time, there's less opportunity to service fans. And similarly to that, there's less time in between innings to ensure that fans are getting their items and getting back to the game. So fans are still, want to get all the novelty of a baseball experience, go to the concessions, but there's also a lot of fans that don't want to miss part of the game. So how do we manage that, given our system that we have presently? So now we want to examine, how do we determine the right amount of, how do we determine what type of concession to operate, while also maintaining that fan experience? And similar to the last one, you could think of a number of different factors that would take place in this regard. And we'll focus on a few today, but certainly this is something to consider as you go along. So as a fan enters into a concession area, what is going to be the order size and the content? That's going to impact things. Also the service time. It may take a bit longer to get an item from the grill than it would be from the fridge or the cooler. Also similar aspects as far as queuing behavior, and maybe if the line's too long, we're going to leave prematurely. Then as well, maybe if we have weather conditions at play, if it's going to be a particular hot day, there's going to be more likelihood to buy cold drinks. Similarly, if it's October baseball, maybe more hot beverages are going to be needed. So all those different aspects play a part in these systems. And really that's where the simulation notion really sheds light on all those different factors at play. So with that in mind, we'll now focus towards the baseball scenario. So in this case, we're going to focus on one section of this ballpark, trying to determine how this section is going to be best serviced from a concession standpoint. So consider that the 6:41 pitch, and when we initialize, we'll assume that it's going to be a sellout crowd. So our crowd is gathered into the stadium and everyone's in their seats at the beginning of the game. And now we want to see, given that the game has started, how are we going to best service these fans across the 9 innings? So with that in mind, that's where we will once more set up some different scenarios to study the system by. So as part of also this object-oriented approach, really that allows users to build out a unique library to their given environment. So consider the scenario that we want to have traditional concession stands. So maybe that's what is been done in the past. That is what's legacy and is the most common in historical baseball. So in that case, you'd have your typical service system where fans arrive to a cashier, they take their order, the cashier goes and retrieves your items from the different departments and produces the order to the customer. So that's your traditional means. But especially now in the world of artificial intelligence and automation, the stadium wants to consider adding automation to their ballpark and what that can do for their fan experience. So in that regard, we also want to consider, what if we add a self-checkout market instead of traditional concessions, removing the cashier from the equation? That's where we build out a similar system, and we'd have the walkthrough area where customers would go through the beverage coolers, grab their items, go to the various food departments, retrieve the items from there, and then they'll go to one of the kiosks directly that'll scan their items for them, and they will go and perform the transaction themselves. But even more off of that, maybe even more in the automation realm, maybe they don't even want to have a checkout location. Maybe they want to have their credit card verified on initialization as they walk into the system, and then all of their items are accounted to their particular account as they exit the system. So in this case, customers will walk through the kiosk, the turnstile, verify their credit card, retrieve their items, and walk back out without the need to go and perform that physical transaction. So really, there's echelons and spectrums of the level of automation for each, but especially in the modern game, in the modern era, with all the different automation at the disposal, these are the types of scenarios that are common in reality and the types of things that are being considered on a daily basis. So we can build out all these various markets separately, but what is powerful then in Simio is that all of these different markets now become an object that I can use readily inside of my model. So if I wanted to go and consider at this concourse, maybe I wanted to add in one of those traditional concession stands right here. I can go and drag and drop that object, and now that is readily available to use in the system based on what was previously built. Similarly, if I wanted to examine the self-checkout, I can drag and drop that much like the other objects. So really, especially if you're thinking about all the different departments and areas of the concourse, that ability to build out that template and quickly examine different scenarios becomes a powerful option, so that as you're managing your system on a day-to-day or week-to-week basis, you have the tools you need readily available and you're not recreating each and every time. So that's what we'll see in this system, that as we run this model on this given day, we want to examine all of those different checkout and concession modes and see how does the system respond to each of those. And to do so, that's where we'll start here. And in that case, we're also going to be considering the various aspects of the concession stand. So in this instant, we're going to have 8 offerings at this concession stand, each of which have a price attributed to them. And then as well, we're also going to have fans arrive in various intervals. So we're assuming that in that similar realm of variability, there's a percentage of likelihood of fans exiting their seat and going to the concourse at various innings. So at certain instances, maybe near the end of the game, there's less likelihood to go leave your seat because you want to catch the action, versus maybe during the 7th inning stretch, there's an increased likelihood just because it's a natural time to get up out of your seat as is. So with those different profiles, and again, some of the other considerations we mentioned, we want to see what is the impact of all those different scenarios. So first, we'll start here with our mode of traditional concessions. So when we run this model, we'll see that the system is going to start. Our fans are going to arrive to their seats. So our packed house is there. And now we want to see over the 9 innings how that system plays out. So when we start here, we're going to run the model, and then we're going to see how it plays out over those 9 innings. And also bear in mind that pace of play. So there's an incentive to get fans back to their seat within that 2-minute, 5-second threshold. So as we start here, the system's taking place, the top of the first is going on. At a certain point, once that top of the first ends, our fans will be introduced into the system, and they'll start to go to get their concession items. So when that takes place here in a moment, we will start to see the concessions take place, and now we see the top of the first has ended, and our fans are leaving their various seats, and they're starting to enter into the system itself. So at the center, we see that we've entered into the concession area, and our fans are getting their orders taking place. Our various vendors are taking their orders, going to the area where they need to retrieve the item from, and our orders are being fulfilled. And this can take place over the course of the game itself. If I expedite the speed, we see that as the game progresses, our movement through the system, different levels of rush, we can get an idea of when there's going to be more periods of demand, less demand. So this is more driven off of those variable instances of fan arrivals. So when this runs and we see that the entirety of the game is concluded, we'll take a look at some of those results at the conclusion of the model. So in this instant, this is just going to give us a nice summary view of the different factors that took place. So based on those prices, we saw how many customers went through our system, how much revenue was generated off of those customers, and then a little bit more on the trends that took place. So how many items were there per transaction? What was the average spend? And this is a little bit more on that queuing behavior. So these transactions lost signifies the number of customers that went to the concourse with the intent to purchase, but deemed that the length of the line was not worth the time, and they went back to their seat. And so resulting on a missed sale. And accordingly, based on the average spend, that would translate to additional $1,600 had they been able to get their food more rapidly. And then representing a portion of the game, not necessarily the amount of time is depends. The average amount of customers that spent more than 2 minutes in concessions was 95%. So really, that's a factor that a fan needs to consider as they enter into the concessions is, are they okay with missing a portion of the game? So maybe depending on certain industries, certain environments, maybe that's okay for some, but others, that's going to represent lost sales. And so we also see the spender behavior as well as the amount of revenue that's generated by type and the average time and system. And then if we also want to examine the time and system in buckets, this is showing the different time intervals for how many average minutes a customer is spending in the concourse. So we see that the bulk of the population is in that 4 to 5, 7 to 8 range, and it starts to tail off with even at the significant level of customers spending up to 25 minutes in line. So there's a concentration here, but we see that for these particular customers, these are going to be infeasible, and we want to ensure that there's a better product for that consumer. Then also given those inning variables, we can consider when is the concession going to be more or less strained. So we see later in the game, given that the 7th inning stretch, we see that there's more strain on the system later in the game. Maybe with last call to purchase beer and alcoholic beverages, we're seeing more customers flock at that moment in time. So really, there's a lot of granularity that can be gathered, not just from a system at large. We can also break that down in intervals to see peak periods of when that may take place. Maybe in other sporting events, you can examine things by quarters, by half times. Baseball's unique in the amount of stoppages, but that's also something that is point of concern for a lot of those vendors. And so maybe given all this, given that we have these wait times, that's where we want to now turn towards these different scenarios. So now if I want to consider the self-checkout scenario, I will examine that once more. And now we've pulled in that checkout scenario, and we're going to run that same model, but now we're going to have the same customer traffic flock through this and go through the self-checkout procedure. It's a little bit different in that regard, but now we see that when the customers flow through, I'll turn down the speed a little bit. We see that our customers are walking right through the entrance, retrieving their items, and then they're going to do the self-checkout themselves, removing some of that manual retrieval from the equation that gives power to the consumer to go and do their own transactions. And so when we run this through the full allotment of the game, we can see the impact on those responses. So in that case, now if we want to go back and look at those trends, we see that there's a significant increase. So an extra 100 customers went into the system, additional revenue was incurred. The average spend and the average items was similar, but we see also a significant reduction in the amount of customers that missed a portion of the game, down to 30%. And then as well, that average time in system was lessened by nearly 5 minutes. So from that standpoint, a significant improvement over the present. Then as well, looking at more of our other statistics, we still see that the bottom of the 7th was a straining instance, given that being the peak period of fans arriving. But we see generally that the average time in system is a lot more stable relative to our expectations. And as well, we also see that there's not this significantly less variability on the time intervals. A lot of customers fall in that 1 to 2 minute range, with a few others dipping into the higher periods. And that ultimately lends itself to the final scenario, that being the transactionless concession, which we would anticipate being the most efficient in that regard. So in this case, once more, we'll run through the system, and fans will enter this. They will verify their credit card, go in, and then they will exit all without having to go through a transaction itself. So removes a significant portion of the process for the fans themselves. So we see them moving, and they're waiting to get in. There's a cap on the amount of fans that can enter into the system, but we're seeing the movement through the system in and out, getting those different instances being accounted for. And we fast forward, we'll look once more at our responses and see what we get. So similar level of detail here. We can see that the comparable level in this scenario, specifically the comparable level number of customers, and that's driven by how many customers are leaving their seats. But we see another reduction in the number of fans that missed a portion of the game down to 16%. The average time in system is now down to 1.67 minutes. So some more improvements operationally, getting fans in and out, getting them back to their seat. This relative to the traditional concessions, a major improvement from an express standpoint. And one other thing to point out, and then we'll turn to experimentation once more, is also that ability to visualize. So if I want to run that traditional concessions operation once more, there's also an ability to run in an interactive sense, where if I want to see the activities that took place in the model, that's where I can turn to these resource scans that allow me to examine system behavior in more detail. So filtering down here, what this is going to show us is at one of the registers, here are the fans that have funneled through the system and what activities took place. So we see the fan with its unique ID. An order was placed, and in that order placement took 11 seconds. Their ID was checked for 9 seconds. We see that their ID was checked because they ordered a beer. So the beer was ordered and was retrieved by the tenant. Then a pretzel was retrieved and delivered, and then the customer checked out. So we can capture all those dynamics in one location, so that as you're validating and ensuring that what's taking place is relative to reality, there's a really an ability to do so and get a conclusive result in that manner. So out over the course of the time, and we see that this customer got a burger, beer, peanuts, and we can see that whole operation took 1 minute and 5 seconds to get that customer's order taken. So another way that, especially in all the different dynamics of the stadium, we can ensure that what is being produced is reflective of reality. And then as well, if we look at those transactions, we get our transaction log off of that also is seeing, based on the order ID, what items are being purchased and with what quantities. We get a nice result in that manner. So with all that being said, that's where we would, again, turn to experimentation to see when we run multiple scenarios, run multiple replications. Each of these represent 10 different games, so 10 different game days, each of which have their own unique dynamics. You see that in the long haul, the expected number of customers for each scenario is the most that can be serviced is that of the transactionless concession. And then we see a significant increase over that of the traditional concessions. We look at our daily revenue, our average time in system, and just overall, what is the number of fans that are going to miss part of the game using each of these different services. And so that's another part of the story, but that's where we can take all that analysis and conclude that more directly with looking at our different scenarios to see from a cost perspective, what is going to be the output of each of these. So this is indicative of all the different costs associated with going with each of these decisions. So maybe if I wanted to look at the traditional concessions, if I'm building a new stadium or looking at the costs, this is just an example of a few types of details, but we can consider what is the fixed cost of this scenario. So we see that there's the capital, the installation, training of the staff, our daily variable costs. So these are incurred each day. And then what's it going to look like from a profit perspective? If we annualize that across 81 games of a major league season, we can see what that would be from an annual profit standpoint. That would be in similar level of output. We see that there's a significant increase in price with the automated options, but also we can see that the amount of profit driven from each of those is also increased as a part of that. So we can get another idea of what are we going to anticipate from a output perspective, and that can help us to make a decision on, from a payback period, which decision is going to be best to go with, and what can we anticipate moving forward with each of these solutions, not necessarily focused on a single game day. So really, there's a lot of tools at your disposal is the takeaway here, and these are just a couple types of scenarios that you can consider as a stadium operator, but really thinking about things as a whole, that the ability to build out your system as a digital twin is really a powerful concept that allows you to make these complex decisions with a tool that is ability to match that complexity in reality. So with that, I will pause and see if there are questions.